The last unit in Chemistry 20 is called stoichiometry. And stoichiometry is the process of calculating the amounts of reactants and products that are involved in chemical reaction. Throughout this unit, you'll notice that a lot of the steps or the calculations that you're doing are things that you've done in previous units. The new part of this unit is the idea of putting all of these together in a certain sequence that allows us to do these specific calculations. Some of the assumptions that are important for this unit and some of the previous units that we've done need to be considered overall in chemistry, but are not necessarily really important in this unit. However, you should be aware that these are assumptions that we're making as we're doing the calculations. The first one is that the reactions are spontaneous. So as soon as we mix together the reactants, products are formed. Second, the reactions happen quickly. So these aren't things that would take days or weeks. When we're doing our calculations in our timing, we don't have to consider that. Third, reactions are quantitative, means that they go to completion. So we will assume that more than 99% of our reactants change to our products. And the fourth is that the reactions are stoichiometric, meaning that we can use those whole number ratios in the balanced reactions as part of our calculations. Another thing to keep in mind is that usually when these reactions are done in a lab or in industry, more than one of the reactants is added into the process. The one that is added in excess or more than is required actually doesn't dictate how much of the product you get. The limiting reagent, the one that's completely used up in the reaction, is the one that actually allows us to predict the products that are being made. We'll come back to this idea of excess and limiting reagents later in the unit. For right now, just be aware that you might see these terms. All throughout these stoichiometry calculations, there's really just 4 steps that you're going to be following in this certain sequence. First thing is to write a balanced chemical equation. The second is to calculate the moles of the given or the known substance. So one of your compounds is going to give you a mass, a concentration, and a volume, or maybe the volume of a gas. That is your given or known. That's the starting point of your calculation. The third step is to use the mole ratio to calculate the moles of the required or unknown substance. The mole ratio is going to come from the balanced equation that you did in step 1. Whatever you're looking for, whatever the question is asking you to solve, is your required or unknown substance. The last step is to calculate the amount that you need. So that might be a mass, might be a volume of a gas. We'll see all kinds of different examples where you need to calculate different things. The first part of stoichiometry that we're going to look at is gravimetric stoichiometry. And this is calculations that involve masses of reactants and products. So let's do a couple of examples so that you can see how these 4 steps work out. Water is produced from the formation reaction of hydrogen gas with excess oxygen. If 2.58 grams of hydrogen is used, calculate the moles of oxygen that are required. So looking back at your notes, the first step we need to do is write the balanced equation. So we want to do a formation reaction of hydrogen and oxygen. Hydrogen gas is H2 and oxygen gas is O2. We're making water, so that's H2O liquid. This needs to be a balanced reaction, and this is going to require 2 hydrogen for every 1 oxygen, and we'll make 2 water. It also might be a good idea to write down the information in the question underneath your balanced reaction. So in this case, what we know or what we've been given is the mass of the hydrogen, which is 2.58 grams. We're calculating the moles of oxygen, so let's put an N equals question mark under the O2. So there's step 1 of our stoichiometry. Step 2 is to calculate the moles of our given substance. So the only thing we can calculate moles from is the hydrogen gas. So we're going to calculate moles of H2 using the 2.58 grams and the molar mass. So we want moles over top of grams so that we end up with moles as our final unit. Hydrogen gas has a molar mass of 2.02, and so this calculation gives us 1.277 moles of H2. It's a good idea to label your units with the compound or substance that you're working with at the time. Third step says to use the mole ratio to calculate the moles of the substance that you're looking for, the required. So in this case, we require oxygen. So we're going to calculate the moles of O2 using the molar ratio. So starting with the 1.277 moles of hydrogen that we just calculated, we're going to multiply by a mole ratio, and the values for that mole ratio are going to come from the balanced equation. We're trying to cancel out moles of H2, so we're going to put the moles of H2 on the bottom. We're ending up with moles of O2, so they go on the top. So 1 mole of oxygen for every 2 moles of hydrogen is what we want in our ratio. And that calculation gives us 0.6386 moles of O2. Looking back at the question, it says to calculate the moles of oxygen. So in this case, we don't need to do a calculation for step 4. We were only asked to calculate as far as moles, so we're done. The only thing we might want to consider is significant digits. And so now we can say moles of O2 is equal to 0.639 moles. In the second example, we have a solution of sodium carbonate that contains 0.4327 grams, and that's mixed with a solution that contains excess silver nitrate. Determine the mass of the precipitate that forms. So again, if we follow the 4 steps, first thing we need to do is a balanced reaction. Sodium carbonate is Na2CO3, and that's a solution, so we can write aqueous for the state. And that's mixed with a solution that contains silver nitrate. That's AgNO3. We have 2 compounds in solution, so this must be a double replacement reaction. So Ag2CO3 is one of our products, and the second one will be NaNO3, sodium nitrate. If you check on your solubility table, you should find that the silver carbonate forms a solid. It has a low solubility. And the sodium nitrate is aqueous. It has high solubility. So balancing this out now, we would need a 2 for the silver and a 1 for the sodium carbonate and a 2 for the sodium nitrate at the end. We know the mass that's dissolved of the sodium carbonate, 0.4327 grams. It's asking to find the mass of the precipitate, and the precipitate is the solid, so we're looking for the mass of the silver carbonate. We can now move on to step number 2, and that's calculating the moles of our given substance, which is the sodium carbonate. So moles of Na2CO3 starts with 0.4327 grams, and we want to multiply by moles over grams, so the molar mass. So 1 mole over 105.99 grams. And that will come out to 0.004082 moles. Step 3 is to use the mole ratio to get the moles of our unknown substance. So our unknown is our precipitate, it's silver carbonate. So using the moles that we just calculated above, which is the sodium carbonate, we want to multiply by a mole ratio, and we want to end up with moles of the silver carbonate, so they need to go on top. We're canceling moles of sodium nitrate, So they're going, sorry, sodium carbonate, so they go on the bottom. And back up in the balanced equation, we see that that's a 1 and a 1. You still have to do this step in your calculations, even if you get the same number mathematically or numerically. The important step is here that we've actually done a conversion from the moles of sodium carbonate to silver carbonate. Last thing is to calculate what we need, and that is the mass of the precipitate. So now we're solving for the mass of Ag2CO3. So using the moles, we can multiply by grams over moles, and that will give us grams overall. So 275.75 is the molar mass we want to use, and the answer, with the correct number of significant digits, comes out to 1.126 grams.